Hi there, and welcome. Today, we're going to crack open the engine behind everything from 3D graphics to AI, matrix multiplication. We're going to get our hands dirty, break down the core math, and then see how to translate it step by step into C code. So here's the game plan. We'll kick things off with the big "what is it?" question, and then we'll get to the one rule you absolutely positively cannot break. After that, we'll learn the actual calculation, what I like to call the row-column dance, and then, the really fun part, we'll turn all that math into C code and decode the loops that make the whole thing work. All right, let's dive right in. First things first, when we talk about multiplying matrices, what are we actually doing? On the surface, it sounds simple. You take two matrices, you do some math, and you get a new one. But here's the catch, and it's a big one. You can't just multiply the numbers in the same spots. Nope, there's a very specific, structured process we have to follow. In fact, before we can even dream of multiplying a single number, there's a critical checkpoint, a non-negotiable condition. This is what I call the golden rule. And here it is. The number of columns in your first matrix must be exactly the same as the number of rows in your second matrix. So if matrix A has 3 columns, matrix B absolutely has to have 3 rows. If they don't match, the whole thing's impossible. You just can't do it. Game over. Let's look at it another way. Say matrix A is m by n, and matrix B is n by p. See how those inner dimensions, the n, have to match up? It's like they link together and then cancel each other out. Because the new matrix you get is going to take its shape from the outer dimensions, becoming m by p. Okay, so our matrices are compatible. They're allowed on the dance floor. Now what? How do we actually figure out the numbers for our new matrix? Well, it's time for the row-column dance. This image just lays it all out perfectly. To get the value for any single spot in that final matrix, you take one entire row from the first matrix and one entire column from the second. You multiply their matching elements together, and then you add all those products up. That's the dance. Let's walk through it nice and slow. To calculate the very first element of our result, we grab row 1 from A, that's 1, 2, 3, and column 1 from B, that's 10, 20, 30. Then we just pair them up, 1 times 10, 2 times 20, and 3 times 30. That gives us 10, 40, and 90. Add those all together, and bam, you get 140. That's our first element. Okay, so we get the math, right? We know the rule, we know the dance. But trying to do this by hand for, say, 1,000 by 1,000 matrix? No way. This kind of repetitive task is exactly what computers were made for. So how do we write the blueprint for this in C? And that's the real question, isn't it? How do you tell a computer to do this dance over and over and over again for every single spot in the final matrix without missing a beat? Well, the answer lies in the loops. And here is that blueprint. Pretty straightforward, actually. First, you declare some arrays to hold your matrices. Then, super important, you put in a check to enforce that golden rule. But the real heart of the machine, the engine that does all the heavy lifting, is a set of 3 nested loops. And after that, you just print out the result. So let's pop the hood and take a closer look at that engine. Because if you can understand these 3 loops, you really understand how to code matrix multiplication. This is where all the magic happens. Think of these first 2 loops, the I and J loops, as your navigation system. Their only job is to pick a destination. The I loop moves down the rows of the final matrix, and the J loop moves across the columns. Together, they're just pointing to a single cell, saying, okay, right here, we're going to calculate the value for this spot now. Now, once I and J have picked a spot, the inner K loop gets to work. This is the loop that actually performs the row-column dance. It zips across the selected row in matrix A and down the selected column in matrix B, multiplying the elements and adding the result to our total for that one specific cell. So to put it all together, it's a perfect system. The I variable locks in a row for matrix A. The J variable locks in a column for matrix B. And then the K variable is the worker that travels along that row and down that column, doing all the math. It's a beautiful little machine. Okay, let's pull back for a second. We've gone from the high-level math all the way down into the nitty-gritty of the code. Let's wrap up with the big takeaways and the hidden cost of this incredibly powerful operation. If you remember nothing else, remember these 4 things. 1, the golden rule. Columns of the first must equal rows of the second. 2, the final size is the rows of the first by the columns of the second. 3, the engine in your code is going to be 3 nested loops. And 4, it all boils down to that formula, the sum of products. Now, about that cost. Because we have 3 loops, one inside the other, the time it takes to run this algorithm is what we call O of n cubed. What does that mean in plain English? It means if you double the size of your matrices, the calculation takes about 8 times longer. It gets out of hand fast. This process is computationally very, very expensive. And that leaves us with one last really fascinating question. If this standard method is so slow and expensive, how on earth do our computers and game consoles multiply the absolutely massive matrices needed for real-time graphics and modern AI? Well, the answer involves much smarter algorithms and powerful, specialized hardware. And that is a fantastic topic to dive into next time. Thanks for joining me.